All right, so I want to talk today about limits. And as we study calculus, one of the things we want to understand is kind of where limits fall in relationship to our entire study of calculus. And I like to picture it kind of like this, okay? We have this overarching idea of calculus. And there are two main things that we do in calculus. We find derivatives and we take integrals, okay? And we could call those kind of the two pillars of calculus. Here's some notation for derivative, and here we have the integral, okay? Those are both derived from the initial concept of the limit. So I like to think of the limit as kind of the foundation behind or beneath the rest of calculus, okay? One of the difficult things mathematicians had to face, and particularly Sir Isaac Newton and Gottfried Wilhelm von Leibniz, they were two mathematicians who lived about the same time, and they both discovered various elements of calculus somewhat simultaneously. And it's kind of a big debate as far as who developed calculus, because historically we can tell that Newton came up with a lot of the ideas first, but he never published his work. Leibniz came up with the ideas, I think, about 15 years after, but published his stuff right away. And then Newton kind of saw it and was like, oh, I've had that for years, and then he published. So there's kind of the debate as to who should get credit, and really both of them should, because they did the work independently. But Leibniz actually developed a lot of the notation that we use today, like the elongated S there for the integral and whatnot. But those two concepts are both based off of this concept of the limit. Historically, at one point, they were using something that they called infinitesimals, trying to get things as smaller and smaller and smaller, infinitely small. And that kind of gave rise to this concept of the limit. Okay? So, first of all, let's define kind of initially what we're doing with the limit. We'll look at kind of what that means, and a little later we're going to actually have a little clearer definition or a more formal definition of what a limit is. Okay? But a limit, in a basic sense, is the value that the dependent variable approaches, and that's usually y, as the independent variable, which we often use x for, approaches some fixed value or infinity. Okay? Now there are a few key terms or key words in this definition that are important to note. Okay? I'm going to darken that up so it's a little easier to see. Okay. First of all, one of the key words in this entire discussion on limits is this word approaches. It's the value that y is approaching as x is approaching a specific value or infinity. Okay? Now approaching just means getting closer to. It does not have to actually equal that value. Okay? In many cases it will, but as we'll see here, other cases it will approach it, but at that exact point, maybe it's undefined, or maybe it actually equals something else, depending on the situation. Okay? So that idea of approaching is very, very important. Okay? Another thing here is this term of value. Okay? For a limit to be defined, it has to approach a specific value. And as we'll mention in a minute here, this is where some people disagree a little bit, and we'll we're going to follow the way the AP and also the IB interpret this, okay? But we'll talk about that in a sec, okay? Now, we can use limits, this concept of the limit, to find the slope at a point on a curve. Those of you in pre-cal honors last year, at the very end of the year, when we looked at limits a little bit, we did this, and we were finding the derivative, okay? That concept of finding the slope on a curve is finding the derivative, okay? Which we said was one of the two pillars of calculus. And then it's also used to find the area of a plane region bounded by the graphs of functions, okay? So we have some kind of a function, you know, we have this end here and the function is there, and we have this end here. If we want to find the area here, we can do it using a limit, okay? Well, that right there develops into what we call the integral. Okay, the integral in its most basic sense is finding the area under a curve. Okay, so the integral. All right? Now, let's look at what this looks like on a graph. Okay? Here we have a graph of some function f of x. We're going to define this as our x-axis and this as our y-axis, or y. And here the function is y equals f of x. Okay? And then notice here we have this statement here, the y value as x approaches a value c. What we're doing here is we are taking the limit as x approaches some value c of a function f of x. Okay? That's the notation that we would use here. It says the limit as x approaches c of f of x. Okay? Now, let's put some marks here on our graph so we can look at specific values. Okay? And let's talk about actually finding some limits based on looking at the graph. Okay? So if I'm first of all going to try to find, say, the limit as x approaches 0 of f of x, okay, you'll notice here where x is 0, on the left-hand side, you can see our function is actually getting smaller. It's decreasing, okay? But what value is our function approaching from the left-hand side? What y value is it approaching? 3, okay? As we come from the right-hand side, what value are we approaching? 3, okay? So, we would say that the limit as x approaches 0 of f of x equals 3, okay? In this case, it happens to be that point right there at the point 0, 3, okay? Everyone with me so far? Okay, kind of. Let's try some others here. Okay, let's say that 1, 2, 3, 4, 5, 6, 7, 8. Let's say that we're approaching -3. Okay, so the limit as x approaches -3 of f of x. Okay, well here is, if we look at where x is -3, okay, I look straight up here, here's our function, As we come from the left, it's approaching a particular value. Okay? As we come from the right, it's approaching the same value. So what would we approximate that to be? Yeah, about 4.5. Okay? Again, we're just approximating here, but we would then say that the limit as x approaches -3 is 4.5. Okay? Now, let's look at two kind of special cases and how those look on the graph. Okay? Over here, you can see a place where our function stops, and let's say that there is a closed point there, and then it jumps down to here, and we'll say it picks up right there and then continues on. Okay? So for some reason our function just jumped down. Okay? Now, this is at 1, 2, 3, 4, 5, 6, 7, 8. Okay? So the limit as x approaches 8 of f of x. Okay? Well, if we come from the left-hand side, it's approaching about 2, right? It's approximately 2. Okay. From the right-hand side, however, as we approach 8, our y value obviously is approaching whatever that is down there. Let's say that that's -1, 2, 3. Okay? So on the left side we're approaching 2, but on the right side we're approaching -3. So in this case, because we're approaching different values, we would say that the limit does not exist. Okay? We could just write DNE. Does not exist. And again, the reason is because we're approaching different values from the left and the right. Okay? So that's one kind of special case. Question?
What's the 3 rule that it does not exist? One is like they go to different points. One is oscillation, and what's the other one?
If they go to different points, oscillation, or it goes to infinity.
Oh.
And that's actually the next one we're going to look at here. We'll summarize those 3 rules too. Okay, let's say we wanted to find the limit as our last one here, x approaching -6. Okay? X is approaching -6. Well, if you look at this, what do we have at -6 on this graph? An asymptote, okay? We've got an asymptote. And from the left, you'll notice it's going up to positive infinity. From the right, it's also going up to positive infinity. Okay? So, you may be tempted to say the limit is positive infinity. Okay? This is where, depending on what book or what professor you have, you'll have some disagreement. Okay? Both are valid points. For our purposes, we are not going to say that it equals infinity. Okay? We can recognize the function is going to positive infinity, and that can be useful. However, what we're going to say is that the limit does not exist. Now, the reason that we say that in this case is because of the way we define the limit. We're saying that it had to approach a value. Okay? So, because it had to approach a value, we would then say it does not exist, because infinity is not a value, it's like a concept that just never ends. Okay? When I was in college, I learned it that you would just say it's infinity, and lots of other people have too. So Understand though, if you look online for extra help for something, you may see places that say, oh, the limit's infinity or negative infinity. We're just gonna say it doesn't exist, because that's what the AP uses, that's the system they use, okay? Does that make sense? Okay. Alright, so this is one way of estimating a limit, by using the graph, and there are times where you can tell very easily, like here at an asymptote or down there at a jump, that the limit does not exist. But getting exact values, you're really just approximating, like we did with the 4.5, you know. We're approximating that it's that, but we don't know exactly. So, what about a better way, okay? Well, that's where this right here, the numerical method for estimating a limit, is useful, okay? We're going to use a table of values in order to estimate a limit for a function that we maybe can't do algebraically or whatnot, okay? Now, one thing here, and we just saw this up here, but this second bullet point is important here. Both limits, as x approaches from the right, okay, and the left, must exist and must be equal, or we say the limit does not exist. This is what we just saw right up here, okay? The limits were not equal, so they didn't exist. And then another thing we need to recognize is that the limit is not dependent, it's independent of the actual y value. Okay? Just to illustrate that real quickly here. Let's say that we have this function, and maybe it's some sort of a piecewise function. Okay? And it goes like this, and there's this point right here. So at 2, 3, there's a hole. Okay? And up here, maybe this point is the point 2, 5. Okay? The value of the function at 2 is 5. Okay? F of 2 equals 5. However, if I were taking the limit as x approaches 2 of f of x, what would that equal? 3. Okay? So, this is what we're saying when we say that the limit is independent of the actual y value. Okay? And again, the key term there is approaches. Okay? Approaches. Okay? So how do we work with finding limits? Okay? First of all, always begin with direct substitution. Now, one question that you might ask is, well, wait a sec, we just said it's independent of the actual y value. It is. So the question becomes, when are we allowed to do that? And we will address that, but the short answer is, if a function is continuous around that value of x, you can just plug it in, direct substitution, and find your limit. Okay? That's the short answer. The next thing is to try to simplify or cancel, or to try to rationalize. This is what you're going to use primarily when you get 0 over 0, which is what's known as the indeterminate form. And what that indicates there is that there's a hole. If you guys remember from pre-cal honors when we did rational functions, we found the coordinates of a hole in a function by factoring it out and then reducing the common factors and stuff. We'll do an example of that here in just a minute. Okay? but the y value of that whole is going to be what the limit equals. And you can actually see, this would be an example where you have a hole, and the y coordinate of that hole is what the limit equals, okay? So that's another strategy we use, okay? Indeterminate form, because we have a hole. And then fourth, this is our last resort, but it's the one that we're going to start with because it always works to at least give us a really good approximation. Okay? It'll always work if you do it right, to get a good approximation. And that is by using the calculator and making a table. Okay? So we're going to look at the graph. The reason why we look at the graph first is to identify, hey, if it's an asymptote, then we know the limit doesn't exist. If there's a jump, we know the limit doesn't exist. But then we can use our table as well to be able to use our calculator as well to make a table. And I'm going to show you how to do that, okay? So if you have your calculators with you, go ahead and get those out. If you don't, please move so that you can see somebody else's calculator, okay? You all will need a graphing calculator for this class, so go ahead and get those out, please. So let's start with this one right here. We're going to, first of all, sketch the graph of x cubed minus 1 over x minus 1. Now, we're going to go ahead and get that graph on the calculator. Okay? So, just as a little review here, on your calculator, you're going to go to the y, hit the y equals button, and then type that in, x cubed minus 1. Make sure you put it in parentheses, divided by parentheses x minus 1. Okay? And then you hit graph, and it should look like a parabola. Okay? Yes.
My graph is, I have a bar graph because I'm in.
Now that we have this graphed, one thing that may not be as obvious is the fact that there actually is a hole at x equals 1. Okay? If you saw the x minus 1 in the denominator, so that should tip you off that 1 is not in the domain. Okay? 1 is not in the domain, which means it's either an asymptote or a hole. And obviously by looking at it you can tell there's not an asymptote there, so there must be a hole there that we're not finding. Okay? Now, how do we find that hole? We're going to look at a couple of ways here, but the first way we'll look at is by finding this table. Okay? Now, your calculator does have a table function on it, and I'll show that to you in a sec, but then we'll look at a little bit more efficient way of doing it, okay? So let's look at this. You can see here above the word window it says table set, or it's abbreviated table set, and then here it says table, okay? So we're going to hit table set, and if I wanted to approach 1, I could set it up to start at 0.9 and go up by 1/10 every time. Okay? Now, if I do that, then I can view the table by hitting second and table. And you can see here, you know, at 0.9, you can see it approaching something until we get an error here, okay? Stay with me. it's getting closer to 1 and we get this error. Here it's getting closer to 1 from the higher values of x, but we get an error. Now, notice here how far apart these are, 2.71 and 3.31. Those are too far apart really to make a good approximation. Now, what I could do is go back and change that delta table and make it like 0.01, but then it's getting complicated here, okay? So if we look back at our table that we were given, you'll notice it starts a little bit of ways away from 1, but then kind of gets exponentially closer. It goes to 0.75, then 0.9, 0.99, 0.999, so it's getting really, really close. Okay? There's an easy way to evaluate your functions once you have it graphed. And that's what I want to show you because that can help you do this really fast. Okay? If you go back to your graph, okay, and you hit trace. Trace puts you on the graph, and notice down here it tells you what point you're on. Okay, if I tried to type in 1 and I hit enter, you can see here y is not defined. That's why no number shows up. But to fill in our table, the first number was 0.75. So if I type in, oh, not 275, 0.75, I know it's 2.3125.
How do you type in?
Once you've hit trace and you're tracing,
Yeah.
then you can simply type in the number and hit enter.
Oh.
Okay? So 2.3125 2.3125. Okay? Now that you're still tracing here, so you can just type in the next number, 0.9, and hit enter. And now it's 2.71. Type in 0.99 and hit enter. And you get 2.9701. Type in 0.999, hit enter, and you get 2.9970. Okay? So think with me here. What value does it look like we're approaching from the left?
3.
It looks like we're approaching 3. Okay? But let's check to the right. Okay? So now I'm going to type in 1.25. And I've got 3.8125. Okay? 3.8125. What do you get when you put in 1.1?
3.31.
3.31?
Yeah. Or if you want to trace, then just
3.03.
3.03? And how about 1.001?
3.003.
3.003? So we can safely, draw the conclusion that the limit as x approaches 1 of this function f of x is 3. Okay? We could say that it's 3. Alright, does that make sense? Okay, so this brings us actually to our more formal definition of what a limit is, okay? If f of x becomes close to a single number, and we'll call that number L, as x approaches c from either side, the limit of f of x as x approaches c is L. And that notation is what that means there, okay? The limit of f of x as x approaches c is L. That's this notation right here. Okay? So we saw this. In this case, L is 3. Our function is getting closer and closer to 3 from either side. So we would say the limit equals 3. Okay? Any questions? All right, good, good. Now, this is kind of a pain, right? Plugging it in, having to type in all those numbers, and how do we know the limit doesn't actually equal like 3.0001 or something like that? I mean,
This is high school math.
this is high school math. Well, we don't do decimals in high school, right? No. Well, this is a pretty good approximation, and you'll notice it ended up being like exactly halfway between those two values that we got on either side. Okay, and that's basically how we're approximating, is we're kind of averaging those. But we do need to do the other values to make sure that we see the trend. Okay? But as you can see down here, we're going to look at how to find it analytically. Okay? Analytically just means by like using algebra and whatnot. Okay? So to do this analytically, you'll remember we talked about holes. And we saw on the graph that this is a hole. Okay? So what we want to do in order to find this analytically is we want to try to get rid of that hole. Cancel out the hole, or so to speak. So if we have x cubed minus 1 over x minus 1, how did we figure out where that hole actually was?
Because it's the denominator.
Okay, what makes the denominator 0 is your x coordinate. Okay, so we know it's the 0.1 something, and that something is going to be what the limit equals. Okay,
Wait, what?
And it's cubed.
I
and it
missed
doesn't
that.
work out.
we know the hole that we're trying to find is the 0.1 something. Okay. If you remember back to when we looked at rational functions back in pre-calculus honors, we looked at how to find what that hole was. Do you remember?
But.
That was horizontal asymptotes. We'll use that later. We actually will use that to rationalize if there are radicals. Like if it was the square root of x minus 1.
Isn't it what value either the denominator or numerator is 0?
Well, that's what 1 is. 1 makes both the numerator and denominator 0.
Oh, wait. I think I know what it is. You have to factor out what it is and then cancel out whatever's left is the whole.
Oh.
Okay, there we go. We want to try to factor out an x minus 1. Do you guys know how to factor out difference of cubes?
No? Yeah, maybe?
Maybe.
Isn't it just x squared minus 1 x plus 1?
If it were x squared minus 1, but we have x cubed minus 1. Do you remember SOAP?
Soap?
Same, opposite, always positive?
I don't know.
Okay. So, when you're factoring difference of cubes, it's been a little while. When you're factoring difference of cubes, to figure out the signs, first of all, you're going to have a binomial here and a trinomial here. And the signs are going to be the same as what you had. So this is minus. And then in the trinomial here, you're going to have two different signs. This one will always be the opposite of what this was. So we have a plus here. And then the last one will always be positive. Same, opposite, always positive. So this is going to be plus, and this is always going to be plus.
What?
Okay?
I didn't.
Now, this is difference of cubes. We're subtracting two perfect cubes. So the cube root is what goes here, and the cube root of -1 is why we have a -1 here. Okay? So, to get this first term, we square the first term here. So this is x squared. Okay? To get the last term, we square the second term here. So -1 squared is +1. That's why it's always positive, by the way, because we get it by squaring. Okay? The middle term we get by multiplying these two together, So negative 1 times x is a minus x, and then we make it the opposite. That's what'll make all the inside stuff cancel out, so we just have the x cubed and the minus 1 left over. So in this case, instead of a minus 1, we'll have a plus 1x in the middle.
Wait, can you write the steps out? Because I might not remember.
Okay? Well, here's the other way. Just to reiterate here, when you are doing this, you take the first term and square it and put it here.
Mm-hmm.
Take the last term, square it and put it last. Take these two and multiply them and put the opposite in the middle. Okay?
Kind of like the factor foil. Kind of like foil, but
Kinda, yeah. We could FOIL it back together. Now, here's the thing. If you forget how to do this, we know how to do synthetic division, right?
yeah.
Right? So if we had a 1x cubed, 0x squared, 0x, and a minus 1, and we want to divide out an x minus 1, we put a plus 1 in the box there. And then remember, add down, multiply over, 1 times 1 is 1. Add down, multiply over, add down, multiply over, and add down. And hopefully you get a 0 there, or otherwise it's not really a factor. Alright, so 0 tells us that it's a perfect factor. And remember, you always lose 1 power of x when you divide. So this was x cubed. So now I have 1x squared plus 1x plus 1, and then this is the remainder. So, see, that's what we ended up with when we factored. Okay? This is why we have more than just this one tool to be able to do the same job. Okay? Sometimes we forget about one tool and we know how to use the other one. Okay? So, we can use this synthetic division to help us factor if we can't remember the pattern. Okay? Alright, so the whole purpose of that was so that, look, we can now cancel out the x minus 1s. And now, if I want to find the limit, okay, the limit as x approaches 1 of what's left over, I can just plug that in because the whole is now gone. So I have 1 squared plus 1 plus 1, which is 3. And now, analytically, I know that the limit equals 3. Okay? So, the limit of x cubed minus 1 over x minus 1 is the same thing as the limit of x squared plus x plus 1, which I evaluate and I get 3 for. Okay. Alright, so now at this point I want to look at 3 cases where a limit does not exist. This was what we mentioned earlier here, okay? The 3 cases where the limit does not exist. Okay, so this is where you'd put D and E. Okay? If you have a graph where it's approaching something different from the left than it is from the right, then the limit does not exist. Okay? If you have unbounded behavior, now what does that mean? There you go, good. It goes to infinity. Alright? This graph right here, 1 over x squared, okay, looks something like this. So as x approaches 0, it's going off to infinity. Therefore, the limit does not exist. Okay? And then C is one that we don't run into all that often. but it is another case where we have oscillating behavior. Oscillating simply means going back and forth between two set values, okay? If it goes back and forth but it's getting smaller and smaller and smaller, we could have a limit that exists. Or getting bigger and bigger, or something like that. But here, this limit as x approaches 0 of sine of 1 over x, what happens here is we have 1 up here and we have negative 1 down here, and as it approaches, I'm not sure exactly what all this looks like, but basically what ends up happening is it goes back and forth, back and forth, back and forth really, really fast, okay? And that's what we have, okay? So, and obviously there is a hole in here somewhere at 0, okay? It's undefined at 0, but it's bouncing back and forth between two set values. In this case, 1 and negative 1, okay? Sine of okay, just so you guys can see a little better picture of this. Okay, that's what it looks like kind of zoomed out. If I zoom in, okay, here guys, you can see this. Who's airdropping? Anyways, it's hard to see here on this graph. Okay? It's hard to see here on this graph, but it's going to end up bouncing back and forth. If we zoomed in even more, you would be able to see it a little better, but that's kind of what that looks like. Okay? Whoa. Okay. All right. All right, to wrap things up here, I want to actually look at this sine of 1 over x, okay? Sine of 1 over x. And you'll notice we have a number of angles that are approaching 0, okay? So let's run through this a little bit. You guys can do this. It'll be a good review of your unit circle. Yes, that's not going away. Okay, so if x is 2 over pi, what's 1 over x?
Wait.
Pi over 2, right?
Wait. Sine is y or sine is x?
I thought that's ice.
Sine is the y coordinate.
Oh, y.
Okay? We're doing 1 over x. So if you do 1 over 2 over pi, it's now pi over 2, right?
Oh, like that?
So what's sine of pi over 2?
Pi over 2 does be 1.
It's 1, okay? It's 1. If I take 1 over 2 over 3 pi, what? It's 3 pi over 2. What's the sine of 3 pi over 2? Negative 1. I heard it there. Negative 1. Oh, come on, guys. Hey, listen, if you don't remember your unit circle, you need to go back and review, because that's going to show up a lot. Unit circle, pi over 2 is up here, remember? That's the point 0, 1. So cosine is 0 and sine is 1. And then down here is 3 pi over 2. And that's the point 0, negative 1. It's coming back slowly, right? Okay. So now, how about 5 pi over 2? It's at 1. How about 7 pi over 2? Negative 1. How about 9 pi over 2?
Negative 1.
and 11 pi over 2. Okay, so listen, hey, remember our definition of a limit, it's what it's approaching. Is this approaching anything? No, it's just bouncing back and forth, guys. It's just bouncing back and forth between 1 and negative 1. So the limit's not defined. Okay? Alright, last one here, and this is what William mentioned earlier. Gentlemen, come on. This is what William was mentioning earlier, where we can multiply to rationalize this expression. Okay? We want the limit as x approaches 0. If I plugged in 0, I would get 0 divided by 0. And if you ask Suri what that means, she'll tell you. Okay? It's kind of funny. Ask her sometime. But here, so we need to do something to get rid of that hole at 0. So we're going to rationalize. How do we rationalize here? Good. Multiply by the conjugate. What's the conjugate in this case? Very good. Square root of x plus 1 plus 1. Okay? Now, if you multiply the denominator out, this is x times square root of x plus 1 plus 1. The denominator comes out to x plus 1 minus 1, right? If we FOIL that denominator, this times this.
Wait, why? Why is
Okay?
No, and then something cancel out, right?
Okay? So, yeah, look. Now we have x times the square root of x plus 1 over just x. And now those x's cancel out.
So, and then,
Okay?
and there's another x, right? There's one.
Oh,
plus-
you know what? Sorry, I lost limit as x approaches 0. Limit as x approaches 0. I forgot my limit there. Alright, now that I canceled that x out though, the hole is gone. And now I can simply evaluate square root of 0 plus 1 plus 1 is 1 plus 1, which is 2.
Wait, if I expand the x into the parentheses, wouldn't I get 2x? Like I got x square root of x plus 1 plus x.
Yes, don't distribute it in there. Okay, I know that's, you didn't do anything wrong, but just so that you can cancel out later, don't distribute that x in. Okay? Alright, and I think you guys are pretty good with the table, but the rationalizing is a little bit more challenging. Okay? So, our limit there would equal 2. Okay? Does that make sense? Are we okay? That's a real good first lesson, right?